crack your computer so that I know you're watching our crew up here. And if you have questions, or you can just raise your hand and ask in the middle of it. This should be dynamic. Nobody should be reading directly off the screen because you should know your stuff. You should also be able to elaborate, yada, yada, yada. Don't worry, I will ask questions. All right, I'm going to cut. Here's the laser. So click your laser. You going to do that? Okay. And if you guys can't see something,
All right. The atomic radius is the measure of the size of the atom from its nucleus to some external boundary by the electrons. Are you all good? All right. Good idea. All right. They find the atomic radius. They can't definitively measure it, so when the atoms are clumped together, they measure the distance from one nucleus to another and half it to find the atomic radius of the atom.
And that picture is showing the different types of atomic radiuses you can find.
As you can see, they're labeled depending on the kind of bonds they have, such as a metallic bond is called an metallic radius, a covalent bond is called a covalent radius, and an ionic bond is called an ionic radius. All right, so like with most of these, it's a periodic trend. So that means there's a general trend that it moves down the periodic table. So what you do is you take your finger like this, and make the upside down L. And as it goes down the column and across the row, your atomic radius is generally going to be bigger. All right, this happens for a very specific reason. If you do that again, sort of like this, as you move down this row, there's going to be a higher level of electron shells surrounding the atom. That just means that the more electron shells there are, the wider it's going to be because it takes up more space. That just means that there's going to be a higher atomic radius as you move down to the higher level electron shells. As you move across the row, the number of electron shells or orbitals doesn't change, but the number of protons does as you move down the atomic numbers. But since there's less number of protons, that's going to mean there's less attraction pulling together the electrons from the outer shells, which means that these electrons, they're free to move around in their own space without the Coulombic attraction of the nucleus pulling them in.
And this equation is just a more mathematical representation. Z equals C minus S, and as you move across the period, S remains constant, but C gets larger, and therefore Z gets larger, and as Z gets larger, the atomic radius decreases.
So S, you're saying, can you tell us more about what S is?
It's the number of shielding electrons, and as you move down a group, which we'll get to later, the number of shielding electrons.
So we'll explain the shield effect on the atomic radius to later slide.
So the terminology, you make sure you're always using period and group terminology, and then you can always describe a nuclear effective charge or energy that the charge is going to be related once you're Coulombic attraction. Charge and charge. Thumbs up.
Good.
6 seconds. And this factor is not the effective ever to decouple.
And the trend down a group, as you go down a group, the atomic radius increases. And as we said, it's because more energy levels are added, which we know is the quantum number n. And as n increases, electron shells become larger, and electrons spend more time farther from the nucleus. And since they're farther from the nucleus, they'll also experience less attraction from the nucleus. So it'll also get larger because of that.
And Nick just explained why as you move down a group, they get larger. But once again, as you move across the period towards your left, the atomic radius expands because there's less protons pulling in electrons towards the center, which means that they have more space to spread out, and the atomic radius is larger as a result.
Sounds good. Okay.
You should be summarizing. Oh, make sure you should on it.
Oh yeah. Oh yeah.
Right, go ahead. That was the second slide.
So when comparing elements from period to period, which means just up and down one column, this is where the shielding effect takes place because you're adding more energy levels, and those inner energy levels shield the outer energy levels from the full attraction of the nucleus. And you should also make sure you don't use the shielding effect as a reason for atomic radius increasing as you go down a period, because shielding doesn't occur for full sublevels, only for adding another energy level.
Say full sublevels, what would that, can you post that actually?
Like S and P and D.
It's like full S,
Yes.
or full P.
As opposed to like when you draw the notes, a single line is what would be considered an energy level. Like in P, there's 3 of them. The P, whatever, is considered the sub-level, right? The line is an energy level.
What are the lines?
Orbitals.
Orbitals. What would be like the entire S, entire S.
And it's just when you move down a period, that's when you have an energy level.
That's your question?
Yeah.
Okay, go ahead.
Exceptions occur when you're adding to a half full P sublevel, which is like when, like the picture shown on page of the
So the exceptions occur mainly to the 6A group, and that's because whenever the electrons jump up from like S to P, they experience the shielding effect. So when the sublevel is half full, such as here, the shielding effect is in full effect. So the shield effect, once again, is when the outer electrons experience a repulsive force from the inner electrons, which counteracts the attractive force of the protons in the nucleus. And this effect is strongest at 6A because at 6A is when the orbitals jump from 3s to 3p.
So not 3S to 3P. It's going to be a little bit more
3P3 to 3P4, right?
Right.
Yeah.
So
Or
when 3P is half full, it's like this because of Fenn's rule. But once you move to like oxygen, you got another electron, and these two electrons repel each other, make the atomic radius a little bit bigger. Right. And I chose that image because if you look closely for 6A, you can kind of see the exceptions occur.
Okay. And is there anything else you guys have for your exception case? Or another slide?
once again, there's graphs.
Is there anything that's significant about the 2A transition?
The The what pay?
The 2A transition. So, because you're right to say the electron repulsion occurs whenever you're in P-block. P-block is in higher energy level than S. But everybody needs to add right now, 2A has a full subshell, right, at the S block. That S block undergoes nuclear penetration, which means that it actually gets more attracted to the nucleus. So sometimes you'll see instead of kind of a more linear trend where it's like increase a lot or decrease a lot. There's a little exception. It's not that it's bigger or smaller than what it should be. It's just that it's more significant change. So it's called nuclear penetration. It occurs whenever you hit like a full S shell, and that's just because S is closer to the nucleus than P is, and so that causes if there's more electrons there, it causes the nucleus to attract more. That's it. Okay. So good job, group. 10 minutes. And next year's ionic radius. Okay. Okay, and I'm gonna close that little Diamond, grab the handout over there. All right, quick transition here, guys. Where's that clicker? You got it? Good. And tell me if we can't see it on this dark background. Let me know if you guys. All right, guys. Ready when you are.
We don't have one.
You want to hand out?
Oh no. Okay. So our thing was ionic radius. And yeah.
So the ionic radius is the distance between the nucleus and the electrons on the outer shell. It's actually very similar to the atomic radius in trend-wise. Okay, so the trend of ionic radius is going from left to right. It decreases because there are more protons than electrons. So that means the electrons are closer to the nucleus. And going from top to bottom, it increases because there are more electrons and protons causing the energy levels to fall.
All right. So this is ionic radius. It's similar because it just with the electrons and how big it is. Because like if the more electrons there are, then the bigger the radius is. Because they repel each other. And yeah.
So anions are typically larger than cations because they have more electrons that cause the electrons to repel. The more electrons that repel gives it a bigger radius.
So I'll explain it from whenever you have your anion, you have more electrons versus what you previously had, you're right, the electron repulsion is what's going to cause that cause the shell to kind of get a little bit larger in radius. But it's also because the nucleus it has lesser effective nuclear charge on those numbers of electrons. So that if you have more electrons, then you're not going to be able to effectively attract all of them as you once were. So then that's going to cause a difference in the shell size as well. So I know that depth charge does still have somewhat of a role here, because we haven't talked about at all. We haven't talked about changing the number of levels. So that is the fact we need to experience in addition to your electron repulsion.
And cations are smaller than anions because they have less electrons, which means they have less electron propulsion.
And correct.
And the depth is higher
So,
than an ion
so how is that higher?
because the nucleus has more effective charge.
The nucleus can change that.
I mean, because it has like less electrons, so
So you can effectively attract the electron count that's currently there.
Yeah.
And then what does that do to the size?
it makes it smaller.
Okay, can there please I'll explain that further.
Let's see.
We'll come back to it.
Okay. And here's a picture I found. It's chlorine and chlorine ion. You know it's bigger because it has that one extra electron. Sodium, and it lost that electron, so it's smaller.
Okay, so the degree of ionization causes. So the degree of ionization, it affects the ionic radius. The environment also affects the ionic radius because depending on the type of environment.
She means the number of electrons lost. Some things are going to be losing one electron, two electrons, three electrons, or gaining, vice versa. So that might cause a difference in the actual size of the ion because it's a multi-electron loss system.
So the ionic radius is very inconsistent. So depending on the type of environment, it can change.
When she says environment, they mean something like bonds and atomic bond, coordinate structure, like that.
And some exceptions are noble gases because they already have 8 valence electrons, so they don't need a bond. And ionic radius is consistent and may vary based on the environment. And covalent ionic bonds sometimes means that the ionic radius is abnormal. Yeah, sorry. Here's a periodic table. All right, this is FRQ that's in one of our packets. And question. The question was, within a family such as the alkali metals, the ionic radius increases as the atomic number increases. And the answer is the radii of the alkali metal ions increase with increasing proton because there's an increasing in orbital and quantum number, which is like S and P and so on. 1s, 2s. Yeah.
When you say increasing in orbitals, what's another way to say that more consistent with what we would say?
Sodium, potassium.
Okay, so that question like this is from before. This one has just an example of the group, but they in a new version of the probably say order lithium ion, nickel ion, potassium ion, organic ion in order of increasing atomic radius or ionic radius. So that this question can lead you to that because you can do the same thing but with data versus a general question. Okay, next question.
The radius of the chlorine atom, 0.99 angstroms, is smaller than the radius of the chloride ion, 1.81 angstroms. The answer is chlorine ion is larger than the chlorine atom because the ion has an extra electron, which means repulsion that makes the radius larger.
Hold there for a second. No, so this is the first time we've actually seen it. You know, first one radius or ionic radius, angstroms, kilometers. So A is a little, yeah, it's a little halo. Ask you all this terms and stuff. So you have angstrom with a little a, or you have nanometers. I'm sorry, picometers. Those are picometers. That either way you say it, that's how you usually describe the graphical. I mean the data points here. And in a question like this on our new stall exam, they will actually give you a data chart with probably 3 parent atoms with their ions, and they'll give you the data and a chart versus in a phrasing system like that. And that's going to be something you need to be used to is data analysis, data evaluation, and coming to conclusions of those scientific phenomena. So one more thing to add to y'all, since I think we're at the end here, right? Is this from isoelectric? You need to add this word. You guys add this if you want to on here's some notes for you guys. Thanks. Okay, so isoelectric, what does that term mean? If you watch the video, you should know isoelectric means. Video if you learn. Or if you know words. Same.
Oh, same number of electrons.
Same electron configuration, right. Same number of electrons, same number, or same electron configuration, basically. Give me 2 examples of something that will have the same electron configuration when it forms an ion. Okay, let's go up to group period 2. Fluoride, neon. Give me an ion. One more ion.
Oh, another ion. That's sodium ion.
Okay. And oxygen. Okay. Which of these is smallest? We got oxygen, fluorine, neon, sodium.
Sodium.
Why is sodium small?
It has the most protons, increasing the whole from it's not like
So sodium, it does have the same number of electrons, but sodium, what? You lost an entire shell from sodium, right? You first lost a shell, and secondly, now that you have lost an electron, its Zeph is more effective, so it's like double-sided sword here. You have the energy level difference and the Zeph, the loss of electron. That makes that difference. What about between these two? Because that's a little bit more even playing field here. We've got they're on the same. They both end at neon's electron configuration from the same energy level, so it's not like they change their energy level. So which is smaller? Why oxygen? Why oxygen? No, it's not oxygen. Why not oxygen? Okay, so this one, oxygen, has how many protons? No. 8. Disappointing me, people. Disappointing me. Okay, so you've got 8 protons, and then fluorine has 9 protons. So who's going to have a? Or tell me what that means.
that means
So this one has a higher Zeph, which has more effect on its radius, which would decrease the radius. So second is that this one loses the other counterpart. So this is that oxygen loses 2 electrons. So when you lose 2 electrons, your nucleus is even more powerful almost.
it doesn't lose to it.
Sorry, against 2 electrons. Sorry, I'm thinking of I have another example for, I'm doing calcium here. So I'm looking at it. So this one gains 2 electrons, so this one's our electron-electron repulsion occurring as well. So this one's going to be a little bit bigger. This one's going to be a little bit smaller. Right? Okay. I'll do this other one in a second then. Okay, because my time is up for this group. Next group is electron affinity. Okay, and then passing on this. Throw him down. Yeah, he's passing this up for you. Electron affinity. I just have to make sure I'm adding to y'all's stuff enough so we can all learn. Does everybody have one?
What is it? Formation of an anion by accepting an electron. So when they accept the electron, well, in addition to an electron to a gaseous atom, Coulomb's attraction causes new electrons to be attracted to an atom's positive nucleus. The amount of energy released when an electron is accepted is the electron affinity. So they release energy whenever an electron is gained to the atom.
Let's try to elaborate by explanation on the screen. Okay, so just rephrase, and we will continue to
Okay, so electron affinity is when a gaseous atom and an electron adds on to a gaseous atom, and so it makes an anion. So here's an example of that. And then the units for that is kilojoules per mole.
This is one that we don't talk about a lot in ours. So it's interesting one to talk about. I'm sure you all know, it's like the why it's really
Yes. Okay, so this process is mainly exothermic. So when the electron is accepted into an atom, it helps the atom become like more stable. And once this atom becomes stable, it has a lot of like pent up leftover energy. And this leftover energy has to be released. And the release of the energy causes it to be exothermic.
I want to ask that when she says energy, she says she's needing potential energy. So that potential energy is being released, which makes the energy, the natural state of being atom more stable. It's not chemical energy because it's not really a chemical change, more of a potential energy changes in the chemical.
So sometimes electron affinity is endothermic. This is due to Coulombic electron repulsion, and it's when some of the groups are already stable or full with valence electrons. So to add another electron requires more energy, so it makes it endothermic.
Okay, so pretty much the trends, they increase in exothermic energy across the period from left to right, and then also as they go from bottom to the top.
Okay, and the trend is important because so the more exothermic values, or the very negative electron affinity values, indicates electron acceptors, and then the endothermic, which would be positive electron affinity values, would indicate electron donors.
Do you need us to go back? Okay.
When you say electron acceptors in that manner, you're saying they want an electron,
Yeah.
the other one does not want an electron.
Yeah.
There are two other terms, and I'll write them forward later. If you're really willing to accept an electron, that says that you have more non-metallic character. Non-metallic character, you're non-metals, means you're willing to accept an electron. If you're not an electron donor, we call that metallic character, which you're really likely to lose an electron. And you can see how this kind of relates back to redox a little bit, the terminology anyway, and you can also see how it relates to like properties of those different extreme groups in the periodic table. Go back for last group. Endothermic as right there in the word. only a couple that are, right?
Yeah, there's only 2 groups.
Don't tell us. Electrical functions. We talk about fraction a lot, but we don't talk about repulsion as much. But it also is going to be very repulsive, high amount of repulsion. They are so close. Distance as well. Back to our subject. Is everybody good? Speak now.
The way the graph moves is it increases from the bottom, and HE and NE would be the highest in electron affinity. So as the yeah,
It's fluorine. So right here is the
that's
highest.
right. Noble gases don't have their zero or the kilojoules per mole given off. So fluorine would be the highest.
Yeah, it's just a picture if you want to draw it on the periodic table on the notes.
Alpha group.
Yeah, and then left to right.
So this is just a visual to show like who has the more electron affinity per different atoms and just more of a visual. The smaller ones would mean a smaller electron affinity and the bigger ones would be the larger.
When you say, this is the one that weird, when you say larger, do you mean
More,
larger magnitude, larger meaning?
more
exoplanet?
More.
Or and goes up, you got like,
This is how it starts, and we didn't do the transition method. That's the gap right in the middle. But the noble gases would be this little bit. You can't see it because how high these are, but actually the highest one would be shown by this graph. The highest one would actually be chlorine.
Okay, so pretty much, am I right on this piece? Okay. So pretty much just to elaborate on when it's more stable. Oh. No,
Oh my.
it's okay.
there's not even a
No,
line.
oh, that's hard.
That's not
Oh no.
Oh my goodness.
Look at the presentation. Look at the presentation. They lie. They lie. Okay. Chelsea, you got it?
Can I write
Write
on
on it now.
Wait,
Do it on the whiteboard.
It's supposed to work.
Oh, you just have different colors mixed up.
Well, I'm expecting.
Okay, so pretty much just to elaborate on the, well, that's supposed to be really dumb. It's okay. Ah. So pretty much it's stable whenever it kind of looks like this because all these here are even, and then it could also be stable whenever it looks like this because it's as well even, and there's no different orbital with a different number. But if it was like not stable, it would look something like that, where this one has more than these two.
Why are the two stable? Why are those first two more stable?
Because the orbitals are evenly filled with electrons.
So in this one, when there's a fourth electron right here, there's electron repulsion. Whereas here, since there's not an extra, sort of, it's balanced or evened out.
Three electrons are pretty separate orbitals, right? Space out. And it's the electron repulsion. The next one, actually, despite the electron repulsion in each of the orbitals, it is more stable because octa has been achieved. So S2 and P6. Now, last one is less stable. It could be more stable. It's not that it's unstable. It's just that it could be more stable, and that's where you guys come in. So that's where they're saying make it more stable by giving it two more electrons with uses a lot of energy to make it go to something. Also, you have to click something.
Oh,
It's okay.
So we have a section on the notes for this slide where it said outer orbital, you can change it to sublevel. So sublevel S. So the exception for electron affinity is in group 2. So with magnesium and all the elements. It is endothermic electron affinity because the outer sublevel S is filled with 2 electrons. So it doesn't need any electrons. And then the next exception is group 15.
okay, go back so that they can write.
So tell me in layman's terms why S2 or 2A does not want an electron.
Because its outer shell is the S level, which is already full with 2 electrons.
So it can accept another one, right? Because we have P available. Why does it not want that?
Because that would require more energy and it would make it less stable.
It's only less stable because electrons that are farther away from the nucleus, like P block is farther away from the nucleus than S block, or sorry, P orbitals are farther away than S orbitals. Farther away from the nucleus means your electrons are crazier, you have more energy. More energy is a bad thing, means you're less stable. So if you make it less stable, it's not going to release energy, certainly, if anything, it's being endothermic, like you said. And so it's about thinking about where the electron is in the nucleus.
So the next one, also sublevel P in group 15, so with nitrogen, all those elements. Since the PX, PY, and PZ have 1 electron each, it's already stable. So it's more stable than gaining an electron. So that whole group is endothermic electron affinity.
So their exceptions were just the difference between endo and exo, not really size the number per se, some size differences, but if you don't want electron, you're in the, if you want electron, you're exothermic. If you really want electron, you're a very high number, high magnitude. And then they are chemical gases where
We're full, so octets, so they're also.
they're endothermic or even 0, meaning like they're just not going to accept it. Anything else? All right, so I hope that influences some of your reasoning in my future groups whenever you're talking about it. We'll look at my notes, make sure I added enough for endo. Yeah, you guys got everything. Okay, and I elaborated as we went. Pull out your FRQs, guys. Let's look at those. There are two. There's the periodic trend offset. We will not need until after our last semester. So I want to have you guys look at the FRQs that you can do. Okay. Pull out your packet. Pull out your packet. And I'm gonna let you guys start, but I'm gonna tell you kind of where to go from there. So, packet. Word is taking its time. Oh, Kevin, your life is ruined now. Okay, so note these. These are the ones I know you can do. Okay, 1981. I'll even highlight them here for my viewers at home. 1981, you can do. Deals with wavelengths. Now, 1982 you cannot do yet because it's got ionization energies in it, so I'd skip most of that. 85, you can try. I'll say try, only because there's some background information that we've already talked about that you might have still accessible in your brain. Thank you, Josh and Devin, for doing parts of 87. You can do parts of 87. Ignore the ionization energy parts if you just want to wait and do that one because you want to do it later with ionization energy. That's totally fine. And then the ones with lattice energy, because we talked about lattice energy yesterday. So like there's parts of 94 you can do with lattice energy. And these are going to be explanation-based questions, right? There's not a lot of math outside of Coulombic attraction that you'll be using in your explanations, except for comparing numbers, okay? I'm going to go ahead and tell you to omit, so take out number 1970. We're not doing it. Yeah, I already know these because these are not really in our curriculum anymore. 1970, 1970, both of those. And then we're waiting on melting points for our next group. We're waiting on that. 1971 I'm holding on to because I will go over that one with you guys. I will do it with you. And then parts of 76D you can do. And then electron affinities from 1977. So let's stop there. So no, I don't expect that you will get all these done right now. I want you to get some of them done over the weekend too. That way, next week you'll have little bits to do. Okay, so the weekend homework is the FRQs, most of them that I just mentioned. If you don't get to all of them, just know you'll be finishing them Monday. Okay. And if you didn't finish your FRQs and your multiple choice corrections, make sure those get done to me in there in my box by Monday. Okay. Okay. You guys got 20-ish minutes. Be productive.
Scroll back down.
Yeah. Yep. We're at 85. So I'm highlighting. So I'm glad because I would have forgotten which ones I said. 87. And some of these have some parts that you don't know yet. So only do the ones you know how to do. Okay. 94. I omitted 1970 on both of those, so they're gone. 76D. 77D. Let me stop this recording. Tell them that.